Hello everyone, I am Xiaogang. Let's look at this query now. Before querying, we can actually create a map variable in our level blueprint or any other blueprint. For this ball, we cannot use kids, we will use int. By doing this, we change this to fstream. Okay, if we are in the blueprint here, you should be very familiar with this. Let's take a variable. You'll find an operator here that has add, clear, contents, find, is empty, and is not empty. Kids and lengths, remove, values. So, what method is above? Actually, this kid is add, and add means to increase. This clear means to erase. And simultaneously, it's equivalent to restoring it to the initial state by clearing everything. Whether this includes, then it goes to check for this kid, whether this is empty or whether it is not empty. This gets all the keys. This is the capacity of the current map. This is remove. This gets all the values. Actually, these are some methods that we can use in Blueprint at this time. Then you click Add. Actually, if you double click, it won't jump past this way. If we can skip it, we can take a look. If we can't skip it, then let's ignore it. Okay, then we turn it off and we disconnect it. Similarly, we can use numbers to check how many elements the current container has. Then, if it needs to contain a specific key, we can use contents and then pass in our kids. Then, if it contains this key, it will return true. If it does not contain the key, it will return false. If we know that it definitely has a character inside, we can use this operator to find it. You need to pay attention to this operator. It is not the past index, it is the past kids. This kids and index are actually two different concepts. And then to take this, it means it's not in the order of elements inside. It is the transmitted key data, it's just an array. Then you can return to this spot. It means that what it returns is also this kind of reference. You can modify the value inside it. It means that if you use const, you won't be able to modify the value. If you don't use const, you can still modify it. But please note that it's actually like never crossing the boundary of the book owner. You need to check at this point whether he has this K letter. If our K letter triggers this assertion, okay, let's implement these few things. Okay, back to us. Back here, okay? We'll call it, if you ask though, let's call it cure map. We call it cure map in this place. We are going to declare something like this. Let's just use it. If we use 1, 2, 3, it will definitely cause misunderstandings. We use it 579 based on this equation of R. Because sometimes when you look at the context, it might be a little confusing. So we will write it using a separate function. This avoids any confusion in our context. So at this point, it's obvious that our number is 3. Then we determine if it has 7 and 8. Clearly, 7 is available, but does not have 8. 8 is false. Then, after we make the determination, we go access these 7 and 8. We check if we can get this value. Obviously, we can get the 7, but when we go access 8, it doesn't. It will trigger this exception. So the situation is like this. And then in this spot, here we are using wallet 7. Right? So we need to validate it. If we do it this way, we can do it this way. This spot actually copies the data out. We call it wallet 7 ref. We can do this, and then here we let it equal. Actually, this part still needs more practice. That is, when should we use a reference? When shouldn't we reference it? Copy this word over. The requirements need to be defined based on your business needs. We call it a copy. It was copied. In this spot, we call it referencing RGV. And at the same time, we can also write a constant reference. Clearly, a constant reference cannot modify its children. It can only be read. So obviously, if you do it like this, the compiler will throw an error. Let's delete this first. Look, this error popped up, which proves that we can't write it this way. Let's attach this main logic here. Okay, let's run this now to test these 3 pieces of code. Okay, same old routine. Let's go change our map vector. Okay, this thing we are giving here should be called quit map. So we go to this place to execute it. Are there any ceiling breaks? There are no ceiling breaks. Okay, after we come in, you can see this place. It is 1, right? Okay, and then we have an element here. Its current value is 3, and simultaneously the behavior is 7. But there is no 8. Then we obtain 7 here, no problem. Then we add a copy. So this 7 plus copy, but you can see that in our map there isn't a 7. So now let's reference it. You will notice that after adding it, this one of ours, let me check. It seems like this 7 wasn't added. Let's take another look. The reason it wasn't added is very simple. I made a mistake here. This is normal. I must have misjudged it. Let's run it again. It should be okay now. Okay, let's rerun this section. We'll just let it go down. You can see it here. There are no problems here. See that the original data hasn't been changed. But after we run through this part, you will find that it's called ref. The original data has been modified. Then this place will trigger an assertion. Let's make it try to move 1 step. Okay, and breaking pause has already triggered an assertion. We can scroll down to the bottom. You can see this. This is an asset from RSTAR, an assertion. RSTAR's PTR is not equal to empty. It seems like ours is equal to empty. So you must go in. Then how do we avoid this situation? Then you need to use this continuance to check. That is, if this has bad true, just if there is, when you go access it again. But sometimes this can be very troublesome, right? If doing it like this is complicated, it means that you essentially need 2 lines of code. You first have to check and then retrieve it. So actually Albert provides a find. The find function can search the row behavior and then return a pointer that points to this element. If the map does not contain this key, it will return a null pointer. On the array map, use the pointer returned by find. It is also an array. It means you cannot modify this pointer, right? And then the pointer, remember that there are 2 ways to add const to a pointer. One is when const modifies the value pointed to by the pointer, and that value cannot be modified. Another is when const modifies the pointer's address. This square has 2 consts. Remember not to confuse this C++ pointer syntax. Okay, let's verify this first. We can introduce it next. Because this font is quite special. Okay. We will give it a font map on our side. I had a strange experience before. If you are an empty man and don't go through it, there will be problems. Okay, as for here, let's look at this code. And then let's first try looking at 7 and 8 here. Then we can click on this to take a look. We found that this value is related to this value. Which means, and once you find it, if you con, then it will fail. What will fail? After you make changes to this map, it will become invalid. So when referencing this thing, you need to be quite cautious. This reference might become invalid, because whether it's a pointer or a reference, after this map changes, you will have to acquire it again. Okay, if we assume here that we haven't added it now, let's see if it will, what kind of action it will execute. A result like this, we call it find paste. The count of this element is 0 now, right? We just added it, so let's simply validate this. Actually, in this area, there is a very common way to do this. Sometimes we do it like this. Because it's a paper needle, we can actually write it like this. If we flip the ptrt, if we can find this element, we will print a log here. For example, we would do this. Still log temp. Actually, you can simply wrap this code. Because you will find that sometimes these first few attributes, they are fixed and unchanged. If we directly enter the kn value without the plus sign, we can just input it like this because our key value is currently an int value. So we will simply provide a 7 here. If we directly reference this pointer, we need to write 2. This part is a bit special. Right, so this area needs to be... Let me show you. Why do we write 2 here? Because it itself is an f string. You convert it to a tchar. You now add a new one. Then you mean a pointer like the previous string. Then you have to cast it twice. Okay, let's activate it now. Let's still go to this spot. Let's find the map here. Okay, let's flatten it using Q. What is Q? Q is actually this. If you have some tools, it can help you connect the blueprint lines into straight lines. We don't use this tool here, so we do it ourselves. It's equivalent to horizontal alignment, vertical alignment. It's just like our Word document. If this spot is empty, we will find it. Take a look. This area doesn't seem to have any issues. It wasn't found. That's normal. Okay, you can see that this area is just a null pointer. And then it prints here. We can scroll all the way down. Okay, this proves that using it this way is perfectly fine. As you can see, this place is because it has already been absorbed, occupied. It actually finds this element. You can see that it prints out here. This is a simple use of the template. This proves that operating on an empty map here has no problems. My previous issue might have been due to multi-threading, because, as you know, tree A and T A P A P A are not thread safe. If you have many threads operating on this TMap and TRA, simultaneous operations can trigger this conflict. So it might have caused a problem when I modified this map back then. How do you resolve this kind of conflict? There are 2 ways. The first way is to use locks between threads, meaning when one party modifies this container, then the other party knows that you are making changes. So they wait until you finish modifying, and then I can modify. Of course, the first method is highly not recommended, because after you add a lock, it will cause this kind of blocking. Sometimes locks, if the lock you implemented is not designed well, it might lead to a deadlock. It's possible that every time the main thread, I have another thread that needs to update this data, I have to wait for it on the main thread every time, which causes the main thread to freeze slightly every time, or freeze for twice as long. In a situation where it freezes for tens of milliseconds, that's a huge waste of performance every time. How about the second way? We can use some thread-safe containers. We can do it roughly like this. What about the third method? We can use some non-locking methods. Then we use some other methods to design the interaction. It's something like a message pump. We send a message into the main thread's messaging class. So let me add a small supplementary point for everyone. Okay, then let's continue looking further ahead. Okay, so in this spot, it means that sometimes even if you query it, until so you would do this. In this way, you are doing an extra unnecessary check on the code. So is there a way to, let's query it. If there is, we can use it. If not, we can add a default one. So it means using FindOrAdd like this. But you can also use FindWave, no problem. And then this FindOrAdd, it provides a reference to the associated value of this value. If the value doesn't exist, it will return a newly created element. Just given the key and build the value. Then these elements are further mapped. Then note this FindOrAdd. Its R shouldn't be confused by this name. It cannot be modified. It must be modified. Therefore, it can only be used for this type of very bright mapping. Just don't add const. And FindWave is a value copy associated with a given value. If the given value is not found, it will return the default constructed value. Then the difference between FindWave and FindWave is, it won't create new elements. It can also be used for long data mapping. It can also be used for non-long data mapping, even if the key isn't found, or if you didn't have it to begin with. FindWave will add a FindWave for you, so they don't need to check this value. Is it blank, or is it an empty pin? Or are they some empty ones that can be used safely like this? If it's a little complicated, we'll attach it here. Let's take a look. We still use the regular line version. We call it Send Advanced. It is equivalent to using a map one step higher. Okay, we still need to make a map here. We just add an element here. Then at this location, it's like searching for whether there is something corresponding to the 7th key. It seems that it exists. Let me show you. Find a value associated with this KID child. If it doesn't exist, add a default one. It returns a reference. Okay, no problem. And then at this point, we added the N8. Actually, there is no 8. Then this place will return a reference. If we don't have it here, we change it. We change it to a, because we know it doesn't exist. We give it a new 8B8. This way it is implemented, but you must pay attention when you do this. Then it will be invalid. If you then perform some other operation, then this place uses FindRef. We can see, perhaps here, we click to look. Find value associated with a split type, and note that you'll notice it returns a value type. It's no longer a reference to the value type. So here we are going to do something like this. We set it equal to 998. You'll notice that it didn't actually add successfully, right? So then, and actually if you reference this area, this section will fail to compile directly because of the value that Leo provided. It is actually a right value. That means it's a 04 value. But at this point, if you are referencing it, you definitely reference this left value because it's a left value reference. Afterwards, actually, the spot is a C++ value. Everyone can go and review it. It's about values and our values. How left references and right references are used. Okay, we won't emphasize it here. So in this place, you should return an empty one. If I add it here, it won't fail. As for this whole segment, we can verify it for everyone again. Let's re-emphasize the issue of pointer invalidation. Pointers or references can become invalid. It's actually like this. If you use find2d, then your previous pointers or references may become invalid, especially when this backend scales out, performing memory allocation, which results in moving existing data after executing this FindOrAdd. Actually, your reference to RF7, it might fail, but it might not fail. As for the specific situation, I'm not very sure. Yeah, we have to look at its memory, how it allocates it. So you must remember this point. This one is also hard to verify. Okay, let's execute it again. Okay, let's find the array here. Okay, let's execute it here. Okay, you can see that an empty map has been generated here. Can you zoom out a bit? Zoom out a bit. We'll just go down. Add the 3 elements. No problem. Remember that it is currently 579 here. Then this gets 7. 7 is such a reference. No problem. And then 8 shouldn't be able to get it. But for 8, we give it a digital version. It's empty now. Let's look at this number again. You will see that it turns into 4 elements. Now 8 is empty. Then let's modify 8 now. You can see that 8 has actually been modified because it's a reference, right? And there, in this spot, FileWife, this is the value we look for here. Never let it be referenced by this name, even though it's called FileWife, but what it actually returns is a value, as you can see. Then we apply this to the FileWife and perform a simple addition. You will find that the value 7 in this place becomes 998, but the S7 is still this 5798. This place is still like this. Then we make it execute a 6 here. This place will add another 6. Actually, this spot is empty, right? So this spot is freed up. If we free it, we still need to add an A afterward. Let's execute it again. Okay, we've executed it again here. We'll just have it find this location. Let's go down another step. Okay, we can see this spot. Take a look. You can see this spot. Actually here, it doesn't actually add any elements here. Because it doesn't add, it actually searches for, if it finds it, it will give you, it makes a copy of this value for you. If it doesn't find anything, it will only return a default field. So this part is actually a little confusing. I haven't looked at it much. So this FindOrAdd, if it doesn't find it, it will add a value, construct a new value, and then return it to you. The new value it constructs is the key and the default value for you. But this FindWife won't create new elements. It won't create new elements. If there aren't any, it will give you a default constructed value. It only gives you the value of this value. This map won't undergo any changes. You can see we set a breakpoint. And this 6 was not added. So everyone, take a look at this concept of FindWife. Okay, remember this add. It means that if there isn't a value, it will be added. And although FindWife doesn't have this value, it can return a default constructed value, but this value will not be added to the map. So this should be used to distinguish between scenes like this. Then we may need to explain this to everyone. Just briefly explaining it. This part, delete it. It won't be placed in. What is returned is the negative value. What is returned is the negative of the value. The name of this place is actually quite ambiguous. It might be creating a new element. It returns a reference. Okay, it returns a reference. Okay, then let's continue looking at it. Actually, if we look further down, I want to re-emphasize this point. That is, every time you modify something in the map, by adding or deleting things in the map. After these operations, then this UF reference, this pointer, might become invalid. And this key value, it can be used for a setup lookup, meaning that once it has been provided, it will only return a pointer that matches the first key value. If the key value does not exist, it will return this space. Let's take a look. What this means is that if you pass a key, it looks for a key in the map, but it's not there. If it exists, it points to and returns a pointer that points to the key value. Of course, you definitely cannot modify it. Otherwise, what it returns to you is a null pointer. And this uses key lookup. If you search by value, it will be slower because this key is mapped. It hashes based on the key, not based on the value for hashing. And then if you have multiple keys that are the same, the find key might only return an arbitrary key because we know that it's on order. You might find it on the first try. Or maybe you find the last one. So if there are multiple cases, it will just return an arbitrary one. Let's just quickly demonstrate this. We call it a side key map. Similarly, let's call this number over here. Let's call this piece of code. If there isn't this root here, we can do this. Let's do this, right? We can just modify and add this in like this. So the first one should be a pointer to hardhead 3112. Note that hexini means the pointer points to this pointer. Let's verify it. We can take a look. The complete annotation for this final key, that is, finding this. The specified one, take a look. Value, this spot is the value. It's through this value. To find this key, yes, this spot is no darn it. It means item lookup. I mean, just give this value to you. Then go back and return this key. Actually, it looks for this value. Then go look for this key. It searches using this value. This should mean that. Right. Then regarding the timing, here's a linear time because he should be equivalent to. According to this, the linear time that is emphasized here, it's because we are through value. It is actually convenient, right? If you have more elements. The time required for its convenience, the more. This is genuinely comparative. So this spot means this. This is the fat k. It searches for k. That is, by using the correct name, it should be called find key. Find key, find key. It's about finding the key from the value. This should be the correct meaning because our previous search method was, it's actually done this way. By passing a key to find the value, it's basically in the forward direction. So the explanation for this direction is like this. Okay, so let's execute it now. Okay, we finished writing it. Let's run it and see. Okay, let's look for the find key here. This find key is looking for the key. We find the key by using the output value. It might be a little convoluted. Let's set a break. It hasn't been able to connect recently. If it can't connect, It might be because we changed the round code. We need to restart it. Okay, I'm connected on my end now. Let's come in. It's the same in this area. We have a container like this. Then we use fat key, passing a value, and then find this key value. If there is this value, then return its key value. Clearly, we have this value. Then return this key value. Then we pass this value. If it doesn't have this, then what we actually return is a null pointer. So this sentence should correspond to this meaning, that is, searching for the key by value, and then returning the pointer corresponding to the first key's value. If it does not exist, return this null pointer, and then this, according to this fed k, it finds k by passing in the value. Then its time is the current time. It is slower than directly using k to find the value, because finding the value using k is a hash. And if we have 3, we pass in this value, and there are multiple identical k values. Then we return any one of the k values. This sentence is really confusing. I was just completely lost. I'm really sorry. So let's verify this scenario now. For example, I have 7 here, right? We give it a 3, then we give it a 5, and we give it a 10, right? Meaning, we input this value. It clearly has 3 k values. So when we actually look for it, which value does it return? We're actually not sure. So what should we do? In this spot, we often give a k brand test1, and then we go find it. Then we add one, then another, and another. Maybe we don't need that many. We give it 3 elements. We gave it 3 elements, and we just triggered an expansion. Because we know that its initial max was set to 4, give it an expansion. Alright, so after we do it this way, then we can, here are 2, let's see what the return value is. Okay, the in value is 32. Let's give it a equals e. This is just to make it easier for us to set a breakpoint. Let's execute it one more time. Our batch poll has arrived here. It seems like it went a little too far. We should put it above. Let's place it one more time. Here, breakpoint. Let's execute it. Actually, everything up to here is normal, right? Then you can see 3 elements, right? Then 570. The first one, its k value is a straight up 5. The second one, it was not found, which is equivalent to nothing. 0 there means empty, just like an empty spot. You can see, right? It's just like a null pointer. And as for this part, if we search for it, it will find. Let's see who it finds. It's looking for 7, right? Then we trigger the expansion. After we trigger the expansion, it has 6 elements. Let's see who it's looking for. It's still 7, but it might not be 7. It might change sometimes. So considering this part, everyone just needs to pay attention to it. Look, maybe the internal elements might change. So it must be disordered. Everyone must reinforce this concept. Let's continue looking at the next part. These 2 functions are actually the same as the k and value that we demonstrated in the blueprint at the beginning. It will fill in all the k and value from this map. Let us demonstrate it to you. This one should be called get all keys and values. I did nx, didn't add it. Actually, it should be included, but for this side of testing, we weren't very rigorous. It's still like this. What's worth noting is that we often do it this way. This is a very common way to write it. It might not be able to return 2. It cannot return 2 return values. In this case, we have several approaches. The first approach is to take this return value and define it here as a structure. Then there are 2 properties inside the structure. Then you modify this and make a structure, pass it out. There is another way, which is that we take the value we output, use the output value as an input. So we can connect it here. So we will do it this way first. We will disconnect this part first. Then we move the Janet over here. It looks like these two lines are for it. So let's move this declaration up here. We'll just start with this map. And then these two arrays. Then we can click on this. You will notice that this spot generates an array. All k values generates an array, all the values. Then this place will help you clean it up. Look at this, out-of-way entropy. Then clear it into these pairs of ours. What are pairs? You can see here, a set of a key value pairs in a map. Actually, it's this one of ours. Let me take a look. It's nap, right? Right? It's just the element we stored. The numbers of its elements. Right. So, then it will first process this array. To have this capacity, then it performs an iterative loop here and adds them in sequence. When adding, it only adds its value, this value and its key. So you can see that it is const. And here it makes it into, so it's the output, you feed it some data, and then you modify it. After you modify it, it gets it from this side. So this is a very common approach. Let's execute it now. Then we get this result. This phrase might be 570. The value might be this. Mango peppers and this one, papers. What kind of fruit is this? I don't know either. Oh, pineapple. Okay. We will now execute this. It should be xt. That is it. Set a beetle. You can see this spot, right? This area of ours is empty. And then it will clear it for you once more. So it won't be affected. And then what comes out are all of our Ks and all the Y6s. Okay, alright. And then you should try not to think about, it says this is its number one key. It's its number one Y6. Don't do it this way. Wait, don't do it this way. Because it is unordered, it's possible that on your side, all of its K characters and external flows may change. You still need to go through our previous find, or access it through the expanded number. So, that's what I meant. Actually, when we are using blueprint, sometimes we write it like this. For example, if I create a new variable here, we just use this. The int one, and then a map. Here we use f3. In the blueprint, sometimes we loop like this. Because we found that blueprint doesn't have a loop. Although our underlying layer has loops, you can't write it like this. It should just be kids, get all the kids, and then iterate through all the kids. Then through this place, get. Okay, let's see if this place should be finded. Go find it. And this place must exist, definitely exists. You can do it this way and won't need to check. Generally, you won't need to check anymore. Okay, in this place, you can just take and use the corresponding value. Yes, it should be like this and not like this. It's not like this. It's right here at this spot. You take this thing like this and then use this index to read this. Don't write it like this. Don't write it this way. That might be wrong. The result you get might be fine, but if you write it this way, it's incorrect. Alright, the standard approach should be like this. It was done like this. Alright, thank you everyone. Our Q&A session lasted a little too long. It lasted about half an hour.